So let's continue then. Okay, so example 11 says the following. So it says, let F be a subfield of complex numbers, right? So this is something we saw already, but since it's an example, we'll have to at least review, right, what we looked at. So it said, let F be a subfield of complex numbers or a field of characteristic 0. That's fine. And let phi be the space of polynomial functions over capital F. Okay, just a second. Right, and then we consider the differentiation operator capital T that acts, so the differentiation operator, we already know how it is defined, right? And the multiplication operator is just that you take T, you take whatever polynomial you have, you multiply it by X, right? So that is straightforward. And now what we want to do is we look at the differentiation operator first. And we know that it's going to send all the constants to 0, right? So we know that it is singular, right? Singular because the set of things that it sends to 0 has something other than to 0, right? Okay. However, V is not finite dimensional, and the range of D is still all of V. Okay, so the randomity theorem would have said that you're missing out on some of the range, but sorry, some of the codomain. The range will not span the entire codomain, but that's not the case here because it's infinite dimensional. Okay, so it says it turns out that it is possible, therefore, to define a right inverse for D. Okay. So here's an example. So right inverse would basically be that you have some object that you multiply on the right, and that gives you identity. Right. So the claim here is that E is the inverse. And how do we see this? So E is the indefinite integral operator, which is defined as follows. It's just usual integration, right? There's nothing fancy happening. Then, so if E is defined as such, then we know that E is a linear operator on V. This is just known from one can check basically because the coefficients would act linearly. So you can check this part is straightforward. And that E is E is such that D times E would give you identity. Okay. So this we sort of saw last time as well, but one can just suppose this is the polynomial you started with. When you apply E, you're going to get some object like this, right? And now when you apply differentiation, you're going to get rid of this, right? And then you'll get n plus 1 will be true. So all of these things will cancel, you go back, basically. So it is sending the function to itself, right? So this is fine, right? So it's an inverse, okay? So what is it saying? So D has a right inverse. And the crucial thing was that this is surprising because it is the case even if D is singular, right? And that was the non-trivial. So any questions about this? Fine, right? Okay. All right, so let's continue then. Now, going back to operator T, right? So we note that T is in the opposite situation somehow. So let's see what that means. So it says that if x of fx is 0 for all x, then f has to be 0. Right? So this is basically for polynomials. It's saying that if the polynomial is such that x of x is 0 for all x, that has to be the case that f is 0. So therefore, T is non-singular. So T, remember, was what? It was the operation where you multiply by x. Right? So this was the definition of T. And what this is telling us is that the only way that this T is going to give you 0 is if the function itself is 0, right? So what that means is that the kernel has only the 0 element. So the kernel is empty, essentially. And it is possible to find a left inverse for T. So it's non-singular, and so therefore we can find the left inverse. And what is the left inverse? Is I'm sorry, could you lock the thing once you, okay. Okay, so for instance, if U is the operation, remove the constant term and divide by X. Okay, so suppose this is an operation that we're defining. So we're removing the constant term, so we get rid of this. Okay, and everything else, we are going to basically take 1x away from it, right? So this is the operation you get. Then it's clear that U is a linear operator on V, exactly because whatever coefficients you have, they will essentially add. Right? So the condition that you have to check is the following, right? So C times alpha plus beta, the linear operator, right? It is C T alpha plus T beta. And you'll see that because, these coefficients are sort of nicely arranged, these x's are nicely arranged, their coefficients would allow you to check that this condition holds. Okay. So U is a linear operator, so this is fine. And then UT would give you identity, right? Because you basically just removed a bunch of x's from the expression you had, and now you're going to add them. So it's going to allow you to recover the function that you started with. Okay, and right. So how you see this is basically because T is multiplying things with x. So even if so this C0 component would never actually appear, right? Because if you start with some function, say b0 plus b1 x, right? You apply T of f, what do you get? Right? Okay, so you see that it always has x. So whenever you have T acting on f, it would, because it's acting on polynomials, it would always have as a result something that has x. There would never be a constant term. So therefore, when you apply u, it will only remove these the powers of x's, right? Bring it back. Sorry. Say if it's 2, it will make it 1. 1. Because it will always bring you back to the function starting. Okay, so that's why it's identity. All right. Okay, but it turns out that TU by itself is not identity, right? So okay, so this is, let's just check, right? So TU, so U is going to do what? U is going to remove the constant term. So suppose we have acted on, say, B0 plus B1x again. So when we apply U, what would this give us? It would give us B1, right? That's correct, yeah. Okay, and then TU on the same object would give us what? So T was going to do, T was going to multiply, right? No, wait, T was going to multiply? Yeah. So it would give you B1 of x. Right. So you can see that it is mapping B0 plus B1 of x to B1 of x. So it's not an H. Okay. It's a sort of related. Okay. Alrighty. So let's see what was the number of this example? Example 11. So now we're going to continue from example 11. Let's. Okay. So now let's look at another example. So example 12 says the following. So let F be a field. Okay, and let T be a linear operator on F2 defined by Tx1, x2 acting as x1 plus x2, x1, right? That's just the definition. Now, T is non-singular, right? Because if T x1, x2 is 0, we would have that x1 plus x2 is 0 and x1 is 0, right? And the only way this can happen is if both are 0. Is that okay? Yeah, okay. So we also have that T is onto. So why is it onto? So suppose Z1, Z2. So what is onto, right? It has to span the entire, the image has to be, so image of T has to be the same as the codomain, right? So it has to be the same as F2 in this case. That's what we have to check. So how do we check this? One way of doing it is to say that there exists, so we want to say for all, say Y in F2, there exists an X such that Tx equals Y, right? So here what we're doing is we're saying, okay, so yeah, let me use the same notation. So for all Z, right, there exists an X such that Tx equals Z. So they're saying, okay, choose x1, x2 such that, the sum is Z1 and x1 by itself is Z2. Right, so you can clearly solve this and it would give you this combination. Correct? Okay. So in fact, that last computation also gives us T inverse, right, which is the following. Right? So you basically do it the other way, right? You can given Z1, Z2, you can find x1, x2 in terms of Z1, Z2. Okay, so these are like very straightforward examples to sort of get familiar with what is and isn't onto and when things are singular and so on. Okay. All right. So let's continue then. All right. So now in example 11, we saw that a linear transformation may be non-singular without being onto, and that it may be onto without being non-singular. right? That's what we saw, that sometimes even though it was singular, it was still able to span the entire codomain, right? So that was the key, the example with the differentiation operator, right? Even though the kernel is non-zero, it's still able to span the entire thing. And we saw that it can be onto, oh, sorry. It may be non-singular without being onto. Okay, so this is the example with differentiation, right? That it was onto without being non-singular, that is being singular and onto, right? And this was the other example that was, right? Okay. So example 12 above illustrates an important setting in which such things cannot happen, and that is basically with finite dimensions, right? Because finite dimensions, we have the rank nullity theorem, and that clearly specifies that you can't do it. Okay, so we have, so we now state the general result that relates the notions of invertibility, singularity, and being onto for finite dimensional situations. So that's what we're going to do now. So that is the statement of theorem 9. So theorem 9 says the following. So it says, so let's make sure that the statement is clear. Okay, so let V and W be finite vector spaces, right, over the field F, such that the dimension of V is the same as the dimension of W, right? And so now if T is a linear transformation, so if T is a linear transformation from V to W, then the following are equivalent. Then T is invertible, is equivalent to T is non-singular. Okay. T is onto. Is the statement. Okay. So this is sort of a little bit surprising because it's not the case if things were not well, okay, everything in the premise, but in particular, this is a property of linear transformations, right? Because in general, you need things to be so singular. You can non-singular. You can think of it as one-to-one, right? Because you've sort of removed the kernel. And for linear transformations, once you remove the kernel, it's essentially one-to-one, right? Because we saw it sends orthogonal things to orthogonal things, and it cannot send two things to one. Otherwise, you'll mess up the linear dependence of the basis. Okay. So normally we know that for something to be invertible, it has to be both one-to-one and onto. Right? It's only then that it's invertible. For linear transformation, it's not necessary to check all of them separately. Okay. So that's sort of the surprising thing about the structure. Is all right. So okay. So then let's start. So let dimension of V and dimension of W be little n, right? Now from theorem 2, the rank nullity theorem, basically, we have that the rank of T and the nullity of T has to be the dimension of the space, right? Okay. Oh, sorry. How long has that been there? Just okay. Sorry, tell me, okay, next time something like this. Okay, so now T is non-singular if and only if nullity of T is 0. Right? So T is non-singular if and only if nullity of T is 0. That is just essentially the definition, right, of singularity. And nullity of T is 0 if and only if T is injective. Right? Because so remember this we discussed at length that if collisions, that implies there exists non-zero element in kernel, right? In the kernel of T, right? Which means that the nullity is not. This we discussed at length in the last lecture. So basically, we conclude that T if T is if it's non-singular, nullity is 0 and it is injective, okay, which is one-to-one. Okay. Now range of T is W if and only if rank of T is little n. Right? That's what it means for the range to be. So onto means what? That the range is the same as the space, right? So in particular, that would mean that the dimensions. Yeah. Yeah. So this you have to be careful about. We discussed this. So a zero vector has 0 dimensions. Like it contributes 0 to the dimension because the definition was the number of linearly independent vectors. Yeah. So 0 is not, because 0 will never be linearly. So it was one of the questions in the assignment. I don't know if it was graded or not. but that was specifically one of the questions. So that's a good point. If you have a set with just the zero vector, its dimension is zero. Okay, don't think that it has one element in the dimension. Okay. Well, actually, okay. All right. So now, okay, so since T is non-singular, okay, so this part is fine, right? So if range of T is W, then it must be the case, it's equivalent to saying that rank of T is N, right? This is fine, both directions are okay. So one direction is immediate, right? So if range of T is W, then obviously the dimensions will match, right? So dimension of range of T is basically just the rank of T, right? This we know. And this is obviously going to match the dimension of W. So this direction is fine. The other direction we proved that the range has to be, so range of T has to necessarily be a subset of the codomain. What is W? Sorry. W is the, yeah, exactly. So range of T has to be a subset of the codomain, right? It cannot go outside that by definition. And now you know that the number of independent vectors and the number of independent vectors here, independent vectors. So here we know that this is equal to n, and this also equals n, right? So it cannot be a subspace, because if it was a subspace, it would have to have one less linearly independent vector, right? It's one of the lemmas we proved earlier, that you cannot have two spaces be like a subspace. You cannot be a subspace with the same strict subspace with the same number of linearly independent vectors. Okay, so that would imply that range of T actually matches W. Okay, so that's the other direction. Okay, so what do we have so far? We have that range of T is W if and only if rank T is N. And now we're essentially done, right? So therefore T is non-singular if and only if TV is W. Right? So non-singular is from the rank nullity, right? The rank nullity says that yeah, over here. So we know that if it is non-singular, so this thing is zero if and only if this thing matches, and this thing matches is the same as saying that TV is the same as W. Right? Is that okay? No. You can stare at it for a second, okay? I'm not saying anything very deep. I'm just saying that rank of T plus nullity of T is N. So I'm saying if this thing being zero is equivalent to being singular, sorry, non-singular. No, yeah, non-singular. They have the non in the other direction. I always get confused. Non-singular, right? So there's nothing in the. Huh? Oh yeah, sorry, exactly. Thank you. I wrote the other one. Yeah, let me just move the whole thing. So nullity is zero. So what that would mean is that so this statement is equivalent to saying that rank of T, sorry, is the same as N, right? So that is equivalent, and that we just argued is equivalent to saying that the image of T is the same as W, right? So that's what gives you the direction. Okay, and now we have basically all properties, right? We have 1, 1, and we have onto, right? So that means it's invertible. Okay, so you get it. Good. Okay. All right. So now stories. The main important thing to keep in mind is that theorem 9 only applies when you're dealing with finite dimensions. Okay. So you shouldn't apply it when when the dimensions are not finite. And did we assume dimension? Okay, and the dimensions have to be the same, right? That is important, because if it's going from a smaller space to a bigger space, then of course it doesn't even have enough vectors to begin with potentially, right, to span the entire set. Like, so for example, if you're going from say 1 dimensions to like a line in 2 dimensions, right? So suppose these are your vectors here. If you map it to vectors in 2 dimensions like that, it obviously doesn't span the set. So you'll not have 1, 1, 0. Okay. So it turns out that, so yeah, these are the two things. Okay, so finite dimensions at the dimension of V and W have to match. Is everything okay? Or there's only one person on this side? Manual, everything's good? Okay. All right. Shall we move on? Is it okay? All right. So it turns out that one can extend theorem 9 as described below, and its proof contains an alternative proof of theorem 9 as well. Okay, so we're going to state an extended version of this theorem. So here we said that these three conditions are equivalent. Okay, now we're going to state a few more things and say that they're all equivalent. And in the process, we would find another proof for theorem 9, different from what we just did. Okay. All right. So let the hypothesis be exactly the same as it was in theorem 9. And then conditions 1, 2, and 3 are also equivalent to these. Okay, so we have that. So the fourth point is this is so 1, 2, 3. We remember. So 1 was I forget the order. Do you guys remember the order? Third was invertible, I think, right? Invertible. Oh, I think I have it written. Sorry, I forgot. You're right. Okay, it's written here. So the first is invertible, second is non-singular, third is onto. Now the fourth condition is that if alpha 1 to alpha n is a basis for V, then once you apply the transformation, then that is a basis for W. Okay, that's the fourth condition. The fifth condition says that if there is some basis alpha 1 to alpha n for V, sorry, not if, there is some basis alpha 1 to alpha n for V such that when you apply the transformation, it gives you a basis for W. Okay, so these two statements, can you identify the difference between them? Because they look very similar. Okay, so the first statement is saying that regardless of which basis you pick for V, when you apply the transformation T, you will get a basis for W. Okay, so that's statement 4. Statement 5 is saying that there exists some basis in V such that when you apply the transformation, you get the basis for W. Okay, so statement 5 is a bit weaker, right? It's saying that you just need to find some basis for which this property holds. While theorem 4 says that you have to show that for all bases that property holds. Okay, so that is the difference between the two statements. Is that okay? Oh. So right, so let's see then how to do this. So this part is saying invertible implies non-singular. This one is non-singular implies onto. And then I think we'll go from onto to theorem, that is statement 4, and then statement 4 to 5 is obvious. And then 5 to 1 was invertible again, right? Okay, so then we've come full circle with the implications. So that's sort of the strategy. Okay, so 1, 2, 3, 4, and 5. So that's the order. We're going to show this implies like this. Okay, and then of course we have all of them are equivalent. Is that okay? All right. Let's start with the first one. The first one says that okay, so if T is invertible, it has to be non-singular, right? Otherwise, the preimage of 0 will have multiple, there'll be multiple preimages, right? So you cannot possibly invert it. So 1 implies 2 is clear. Is that right? Yeah. Okay. And then 2 implies 3 is the following. So it's saying non-singular implies onto, right? So let's see. So suppose T is non-singular. Then suppose this is the basis for V. Okay. And then T alpha 1 to alpha n are linearly independent vectors in W using theorem 8. Right. Because we said, oh, so theorem 8 was basically saying linearly independent sets are sent to linearly independent sets under linear transformation. Okay, so now since the dimension of W is also n, this is what I was actually saying earlier, but I was saying it quickly, but now we do it more carefully. So suppose since the dimension of W is also n, it follows that this set of vectors is also basis for W. Right? So you have n linearly independent vectors that are in the space, and the dimension of the space is n, so they obviously span the space. We couldn't possibly have. Okay. Now let beta be any vector in W. The scalars C1 to Cn are such that once you apply, so you can use this as a basis, right? So T alpha 1 to T alpha n are basis, so you can express any vector in beta as a linear combination of this basis, right? So that's all we've done, and because it's linear, we can pull it out, right? So we can take the coefficients inside and apply t to that. And now what this shows is that beta is in the range of t, because it's basically proving the statement here that it's a basis, right? So it's proving this. It's saying suppose you take any arbitrary beta, it will show that beta is actually in the range of t, because there is a vector alpha such that when you apply to it, so this shows that t is onto. Is that fine? So it's, yeah, sorry. So here we are relying on the fact that it's basis. I misspoke. So it uses the fact that it is a basis. So T alpha I, the basis for W. Right? And now here we are showing the onto property. Okay, that's the structure. Any questions? Is it okay? Okay. All right. So now let's do the next step. So it says from point 3 to point 4. So it says onto. So what is the name of the person sitting next to you? Yeah, no, I understand why you were asking the question, but I cannot make a decision at this point. So I'm sorry. I know you normally follow and you're probably doing the assignment now, but yeah, I can't. Yeah, I can't make a decision at this point by myself. So are there probably a lot of people are sitting and doing the assignment now, isn't it? Yeah. Yeah, I'm sorry. Yeah, we didn't think of this. Like, we'll be more careful next time. Before the exam, we'll try to not have. We thought that it would help so that you finish the assignment. It'll help you with the exam, but maybe it's not helping with the lecture. Sorry, but yeah, can't change anything at this point. Sorry. Okay. Right. So point 4 to 5 is what is it saying? So point 4 to 5 is saying right. So number 4 was that if right. So we already established, right, that there is a. So 3 to 4. No, we didn't do 3 to 4. Okay, sorry, I missed one step. Okay, good. So now we know that the onto property holds. Now we want to establish that under the transformation T, you get a basis, right? That's what we want to establish. So all we know is that T is onto, that is the only assumption now, and it's a linear operator, of course. And we want to prove that if you have a basis, then this will also give you a basis. So already what is clear is because T is a linear operator, it will map independent things to independent things. So that part is fine. All we have to do is that it spans the range of T, right? Sorry, it spans the. Yeah, okay. So T alpha 1 to T alpha n, they obviously span the range, but we want to show that range of T is the same as W. But I've written which by assumption is the same as W. Yeah, okay. Oh, right, because of the onto property, right? Sorry. So that's the assumption, right? So by the onto property, we know that this also matches W. So this is fine. Now, since the dimension of W is n, we already know this. These n vectors must be linearly independent. Okay, so I think I maybe messed up a little bit. So I was thinking that maybe we could use the theorem, right, that says you map linearly independent vectors to linearly independent vectors, which is what I was saying. But in that theorem, you're assuming that T is non-singular, right? Because obviously you could map everything to 0 and still call it a linear operator. Okay, so my reasoning was not correct. So when I say that, T alpha 1 to T alpha n are linearly independent because alpha 1 to alpha n are linearly independent, and T is a linear operator, that is not enough. Okay, so this is, so let me write on not in general. We assumed it's non-singular. That is the crucial part, which I also missed. Okay, so not true in general. What the statement that if alpha 1 to alpha n are linearly independent, okay, and T is a linear operator, sorry, then in general it may be. So I'll just write caution here. Maybe that T alpha 1 to T alpha n are not linearly independent. Okay. Exactly. So we have to add that property, but here we're not assuming that, right? We're just assuming T is onto, and we're trying to prove it from there. I just had a that it's onto, right? T is onto, yeah. So we're assuming T is onto, and now we want to prove that if T is onto, it's linear, it's onto, but we don't know whether it is singular or not. We want to argue that now if you act on alpha 1 to alpha n, then T alpha 1 to T alpha n span the is a basis for this space. Okay, so what we do know is that T alpha 1 to T alpha n certainly span the range of T, right? Because you started with linearly independent vectors, so and then you can essentially express any vector using the structure. It's essentially the same argument as you can express any vector in the range of T using a linear combination of these guys. Yeah, and that by assumption is the same as the space W, because that's what it means to be onto, that the range is exactly the same as W. Now comes the rest of the argument. Now it says that since the range of W is little n, right, these little n vectors must be linearly independent, right? Otherwise the dimension would be lower and they couldn't possibly span the set, right? Is that okay? Well, right. So that in turn means that these guys are former bases for W. So that is good. Now 4 to 5 is just saying, so okay, so in 4 we proved that regardless of which basis you pick, T alpha 1 to T alpha n is going to be a basis for W. 4 to 5 is a weakening, right? It's just so 4 is only saying that there exists some basis for V such that when you apply T, you get a basis for W. Right? So that is obviously immediately trivially implied. And now we do the last step, which is interesting because you're going from 5 to 1. So now it says, suppose there exists some basis alpha 1 to alpha n for V such that T alpha 1 to T alpha n is a basis for W. So we're at the final round now. So the first claim is that the image of T matches W. That is, we try to prove that T is onto. Okay. And in the next step, we prove that T is 1 to 1, right? And then these two properties together will tell us that it is invertible, right? Because that's all we need for invertibility in general. So that is sort of the strategy. So let's try to see. So we want to prove that image of T is W, that T is onto. So then since T alpha I span W, right? Right. So we already assumed, right, that this is a basis. So T alpha I is a basis for W. So that means T alpha I already spans W. So there's not much to prove here, right? So one can show, as we did before, that the range of T is all of W. Right. So from the fact that this spans, we can show that for every in W, so one can show that the range of T is all of W. Okay, so they're basically saying, yeah, so since we can span, since T alpha spans the space W, right, the range of T is all of W, because we want to say that, so image of T is, so to show something is in the image of T, we want to say that, you know, beta belongs to image of T, then you can write beta as a linear combination of Ci's T alpha i's, right? Because it belongs to, actually, sorry. So suppose beta belongs to W, so then we can write W as a linear combination because this is a basis, right, for the space W. Is that okay? Write as T acting on sum over I, Ci alpha I, and this object itself belongs to V, right? And so what that means is that beta, so that implies beta is in the image of T, right? Which is what we wanted to argue. Is that okay? Is it clear? Is it not? I can repeat if you want. But what was the name of your friend? Karthik, was it? No. Is it clear? Did you get lost? Okay. Sorry, what's your I didn't answer. Say it again. Okay. I can wait if you want. You want to repeat. Yeah, shall we move on? Okay, so this is down that it is onto. Now we have to prove that the null space of T is just the zero vector, right? And this has zero dimension, right? Like we just saw. And that would mean that T is 1-to-1, right? All linear transformations, because you can apply the rank nullity theorem. All right. So now if alpha is some vector as a linear combination, if this happens to be in the null space of T, right, then obviously when you apply the transformation, you get a 0, which would mean that some linear combination would be the 0. And now since T alpha i's are independent, we know that Ci is going to be 0, right? So we know this because T alpha i's are linearly independent, right? And because there are bases for the subspace term. So the only way this is 0 is if the C's are 0, and that would mean that the only way you can have something be in the null space is if it's a 0 vector, right? Okay, so we have established both. We've established T is onto and T is 1-1 by just starting from the assumption that there exists some basis in V that is mapped to a basis in W. That is all we assume, right? And so then we conclude that T is also invertible, right? So that brings us back. Okay, so we basically showed all four. So this is the one that we just saw, and that brings us back to, oh sorry, this is the one that we just saw. 5 implies 1, right? And that brings us back to the book. So they're all equivalent. Okay. Any questions? Okay, shall we move on? Okay. All right. So now we look at, so now we continue, right? The set of invertible linear operators on a space V with the operation of composition provides a nice example of what is known in algebra as a group. So somebody was already asking me about groups because they had, I guess you had discrete algebra, whatever, discrete math earlier. So, okay. So, all right. So although we don't discuss these things in much more detail, we at least look at the definition and see how, some of the things we've constructed actually satisfy the definition. Right. So what is the definition here? Okay, so a group is basically a set G, okay, and it has a rule for associating with each pair of elements X, Y in the group. Okay, so you have X, Y. So there is some group operation that takes X, Y, and it gives you some element X, Y, which is also okay. So these things belong to the group. You apply the group operation, and this will give you some X, Y, which is also in the group. It has to satisfy a few properties. So it has to satisfy that it's associative, right? Doesn't matter which order you compose in. The second is identity, that there is an element E. So compose meaning like you're going to apply the group operation here. So you can write it more, if you want to expand it, you can write it as X. So you can say the group operation, let me write it as op, right? So the operation of XY is the same as operation X, oh, sorry, this is YZ. YZ. Okay, yeah, so what should this be equal to in this notation? The associativity property. So I'm writing the multiplication as op, right? So what should this be equal to? Exactly, op X comma Y. Right? So that's what it means, just so you sort of, because it looks deceptively similar, the notation, but keep in mind, okay. Identity is what? Identity is saying that you apply the operation with X and this object, either on the right or the left, you're going to get X for all X, right? And the inverse is saying what? The inverse is saying that there exists some operator X inverse, such that, so for all X, there exists some X inverse, such that op, when you act on the inverse, or you apply the operation in the other order, you're going to get the identity element. Okay, and the identity element was this, is defined like this. So for all X, is that okay? Okay. Okay. So let us see what kind of an object might satisfy this definition. So we saw that the composition of U comma T to UT, right, which associates with each pair of invertible linear operations, another linear invertible linear operator V, a linear operator on V. The composition is associative, right? Because whether you do this matrix multiplication, basically it's inherited from matrix multiplication in a sense, right? Because we showed the Did we show the isomorphism? We haven't even defined isomorphism, right? Okay, that's I guess it'll come. I guess one can just do it from the actual definition from the beginning. So one can check that this is satisfied. I'll probably write it as homework. The identity operator I must satisfy this for each t. So this we already know is the case. And for an invertible operator, sorry, invertible linear t, there is by theorem 7 an invertible linear operator t inverse such that this is the case. Okay. So now, what was the definition of an invertible operator? So invertible operator, say t, the definition was that there exists a unique element, right? T inverse t, and was it unique or not? I think it was unique, yeah. That this gives you identity. Okay, but what is not guaranteed is that if t is linear, so if t linear, it is not obvious that t inverse is also linear. Right? This part is not so clear. And it turns out that we actually proved, we either proved or we will prove, I don't remember now. Did we already prove this? Theorem 7? Yeah, okay. So we're doing theorem 9, so we proved it already. So we already proved that if the operator is linear and invertible, then the inverse is also a linear operator. Right? I think we saw it last time. Okay. All right. And all right. So now thus the set of invertible linear operators on V together with its with this operation is a group. Okay. So yeah, so it has all the properties, it has associativity, it has identity, and it has an inverse. Right? These are the three things that we need for something to be a group, and it has all the properties. Okay. Now let's look at another example. The set of invertible n cross n. Okay, not okay. This is just my typos, okay, because I'm typing on the computer. I sometimes mess up, but yeah, I don't know why it's a systematic problem. Okay, the set of invertible matrices n cross n matrices with matrix multiplication as the group operation also form a group. Okay, so for instance, 1 0 will not be a part of that group, right? Because it's not invertible, right? Okay, so a group is called commutative if the following, okay, so there's not much to do here, right? So we know that matrices, they satisfy x, y, z, right? Whether you do y, z, or you do x, y first, one can check by just the definition of matrix multiplication. These are the same. And for the inverse as well, right? We know that z inverse z is going to be z inverse. This we already said. Sort of checks on this. Okay. Right. So now a group is called commutative if it satisfies the following. It's x, y equals yx. Okay. So the examples that we looked at, the composition of linear operators and matrix multiplication, these are obviously non-commutative, right? So we have obvious examples where you cannot switch the order and expect the things to match. So one often writes group operation for commutative groups, using this notation. Okay, so we're going to write x comma y as x plus y. So when they're commutative, we tend to use the plus notation. Okay, it's nothing very deep. Okay, it's just convention. So when you are exposed to more math, you sort of know what's happening. So they will write the plus notation, and the identity would normally be given by 0, right? Because x plus 0 is the element that gives you x for all. Right? It's not 1. Obviously, it changes. Okay, and some examples of commutative groups. Obviously, you can just use regular numbers, excluding the 0 number. But you could also take the set of vectors, and they would form a commutative. Okay, and then the addition, the operation is vector addition, right? Because for every vector, you can find the inverse as the vector in the opposite direction. So you sum it gives you the 0 vector. Right? Is that okay? Okay. So, okay, and one can view a field as some sort of a generalized, can one view a field as some sort of a generalization of a group? And that's one last thing that they're asking. So the answer is yes, right? Because the field can be described as a set with two operations, addition and multiplication, right? Which is what we did. Where the commutative group, which is a commutative group under addition, and in which the non-zero elements form a commutative group under multiplication. And you have to follow this distributive law, because now you have two operations, you want to have some kind of distributive. And then, yeah, then there are other things, right? Like there are the more general concepts, like the modules and this, that, but we won't necessarily cover. So you can like relax this commutativity requirement and things change. Okay. All right. Okay. So that sort of concludes this 3.2 section. So we can now start with 3.3. Any questions before we start? Okay. All right. So let's do 3.3 now. So, right, so let us start directly with the definition of interest here. So the definition, yeah, so I think the motivation will sort of become clear as usual as we sort of study the object. It'll become a little bit more clear. Right, so here the definition is the following. So if V and W are vector spaces over F, okay, and you take any map from V to W that is linear and one-to-one, okay, then this is going to be called an isomorphism of V onto W. Okay, so you need two properties. You need the map to be linear and you need it to be one-to-one. And if you have such a map that goes from V to W, we'll say it's an isomorphism of V onto W. Okay. And if such an isomorphism exists, then we would say that V is isomorphic to W. Is the definition of exams? Okay. All right. So let's continue then. So let's make a few remarks. So what is mapping V to W mean? So what we mean by this is that the map T takes the set V into the set W. That is, T from V to W is onto. Right? So you're not missing out on any elements. So image of T, right, is the same as W. Okay. And why does this matter? Because one-to-one and onto for a linear transformation implies that T has T inverse, and that is also a linear transformation. Okay, so you sort of have to be clear. So it was linear one-to-one. And what they mean by, yeah, okay. So this onto word is the important word, okay? Which is I sort of missed it the first time I read it. Okay, so it's linear one-to-one and onto. Okay, that is sort of important because see now previously what we were doing was we were taking in the previous theorem, right? We had dimension of V and dimension of W were the same, right? So there we could say that one-to-one is enough. That one-to-one implies onto. But here we're not making such an assumption, right? We're not saying that dimension of V and W are the same. So now we have to say both one-to-one and onto. Okay, be careful. If you're asked, whenever you're looking at these objects, you have to be careful about whether the dimensions match. And if the dimensions don't match, then one-to-one does not imply onto. Okay, so you have to check. Sure. Okay. So this is what it means. So you're mapping V onto W. So that means that this thing is one-to-one and onto, and that in particular means that T would have an inverse. Right? One-to-one onto means that T has an inverse, and we already proved in theorem 7 that if T has an inverse, then if T is linear and T has an inverse, then the inverse is also linear. Right? This is fine. Okay. So all right. So this is one important thing to keep in mind. That this map T is invertible and and the inverse is linear. The second step is the following. So note that V is trivially isomorphic to itself. Right? Identity map satisfies all the properties. So this is fine. And now it says if V is isomorphic to W via some isomorphism T, then W is isomorphic to V. Right? Why is that? Because exactly. So we have T inverse, right? And T inverse satisfies it is linear because T was one-to-one onto, T inverse is one-to-one onto. We're done. Okay. All right. So okay, so we have this, and basically what we've said is that V is I forget what is the notation. So if relation AB is the same as relation PA and relation AA is true, right? Then we say that this relation is equivalence class, right? Is an equivalence. You know this, right? So this is just the property that if A comma B are related and B comma A are related and A comma A is related, then basically you can think of this relation as just being equivalence. Okay, in the normal sense. T is a linear transformation, right? Yeah, T is a linear transformation. And so that was crucial, right? Because T is one-to-one and onto, we know it has an inverse. And because it's a linear transformation, we also know that the inverse is a linear transformation. Right? So it satisfies the same requirements. Okay. So we can say that V is isomorphic to W, as we can write it as an equivalence relation. So there's no notion of directionality because they're equivalent conditions. Okay, so then we also have this, right? So V is equivalent to W and W is equivalent to Z, then V is equivalent to Z. This just follows from these properties actually, right? Because once you establish these two properties, then you can show that it's an equivalence class. I think so, yeah. Okay. All right. Okay, so in summary, isomorphic forms an equivalence class, and we may therefore say that actually maybe you need this separately as well. No, I think you need that separately as well. Sorry. I think you need that if relation AB is true and relation BA is true, BC is true, then it should imply relation AC is true. I cannot think of a counterexample directly, but yeah, you need the transitivity property, right? So you need transitivity, you need reflexivity. I think that's it. Yeah, and then the order. Okay, whatever, it's fine. Okay. Right. So V and W are isomorphic, as opposed to V is isomorphic to W. Okay, so we don't have to say which is isomorphic to which. They are the same things. So, right. So with all of this, we now state a theorem that shows why the space Fn tends to be so rich. Right. So Fn was like one very specific kind of vector space, right? But why it happens to carry a lot of structure is because one can formally understand it because of the following. So theorem 10 says that every n-dimensional vector space over the field F, okay, so n-dimensional, every n-dimensional vector space over F is isomorphic to Fn, right? So it's saying that anything that you could do in terms of vector spaces, which are of n-dimensional and they're defined over some field F. So that's a very general statement, right? Like you're allowed to do whatever you want. Turns out whatever you do is going to be isomorphic to Fn. Okay. So that's the statement. It's not immediate if you've not seen isomorphisms before, why isomorphisms are a very important thing, but they tend to preserve, distances and inner products and all these kinds of nice things. So we'll see that later. This here. So it says what? It says that let V be an n-dimensional space over the field F, right? And V be alpha 1 to alpha n be some ordered basis for the vector for the space V. Okay. Now, what we're going to do is we're going to define a function t that maps V to Fn as follows. So if alpha belongs to the vector space V, we let T alpha be the n tuple. So T alpha is x1 to xn, okay, of coordinates in, yeah, so basically, yeah, so here, these x1s to xn's are just the coefficients, right? So you have some basis, you're writing an arbitrary vector in terms of this spaces. And now if I recall from chapter 2 that we proved that T is linear, one-to-one, and maps V to V onto Fn. Okay, so we have defined a linear transformation, right? Which is just taking this vector alpha and mapping it to the so in Fn, it's mapping into the vector that has these coordinates. Okay. And we already showed in chapter 2, when we were talking about coordinates, remember we showed that the coordinates are unique, yada yada, all of the properties. And so what we had actually established is, first of all, linearity is kind of straightforward. One-to-one and onto come again from the dimension argument and from the fact that the difference will disappear because they're linearly independent. So you couldn't possibly have two things mapped to the same coordinates, right? Because then the difference would violate the linear independence of the basis, essentially. Yeah. Okay, good. So that's it's a very simple proof, but it's a sort of a kind of a general statement, right? Like it's showing that any vector space of a certain dimension is just equivalent to Fn in the sense of an isomorphism. Got it. Okay, so for many purposes, one often regards. Just give me a second. I'll turn off the light. Let me pause it. Is it okay, guys? For everything, you can see. Is it okay for? There's enough light, right? There's enough light for you for editing. Okay. Well, yeah, sorry, it was just too much reflection on the screen, so it's hard to see what's the two. Okay. So for many purposes, one often regards isomorphic vector spaces as being the same. Okay. Although the vectors and operations in these spaces may be quite different. Okay. So that is one often identifies isomorphic spaces. So what this is doing now is trying to give you some intuition about why isomorphisms matter. It will not give too much intuition, but it's giving some intuition. And it's basically saying that any two vector spaces that are isomorphic, intuitively, we can think of them as essentially being the same space. That is sort of the idea. Now it's going to tell you why that is the case. So it doesn't give you a lengthy discussion, but the approach, this is just saying that it will become clear. So here are some comments. Let's see. So suppose T is isomorphic, is an isomorphism of V onto W. This is T is the mapping, right, the linear map from V to W, which is 1, 1, and 1. Now, if S is a subset of V, then theorem 8 tells us that S is linearly independent if and only if TS in W is linearly independent. Right? So that is just coming from this theorem. Right? It was assuming non-singular, which we, it's 1, 1 onto, so it is non-singular, so that is guaranteed. So here it is saying that if you have a bunch of linearly independent vectors, they're going to be mapped to linearly independent vectors as well. Okay, so if the spaces are isomorphic, under the mapping, linearly independent things are mapped to linearly independent things. So it says, so when you have questions of this form, when you want to decide anything related to S being linearly independent, it doesn't matter whether you look at the set S or TS. It's going to give you the same answer. Okay, so from this one sees that an isomorphism is dimension preserving. Right? That is, any finite dimensional subspace of V has the same dimension as its image under T. Okay, so this is the same. And here's a rather straightforward example that illustrates the point. So consider a set of n tuples, so x1 to xn and fn, that satisfy the system ax equal to 0. Because you have a bunch of x's that satisfy this equation. And you consider the set of all n cross 1 column matrices such that ax equal to 0. Okay, so these things are very, very similar. Okay, so all this is saying is that you take fn, this you're taking a tuple. Okay, so it's just x1 to xn. It's taking this tuple and it's looking at all those such that if you put it in a matrix, you get 0. And in the other case, it's looking at columns x1 to xn, and it's looking at all of these columns that when multiplied with they give you 0. Okay, so a very, very similar statement. One is a row, one is a column. That's it. Nothing very deep happening. It says the first is a solution space of the subspace Fn, while the second is a subspace of n cross 1 matrices over F. Right? So formally they are different objects. Okay. There's a completely obvious isomorphism between Fn and Fn cross 1, which is this. Right? So it's mapping vectors from one to vectors in the other. So one can check that this is 1, 1, invertible, linear, everything is fine. And now what it's saying is that under this isomorphism, the first solution space is carried to the second solution space. So the spaces are mapped, and these spaces have the same dimension. So what it's saying is that if you wanted to prove a result about the dimension of the solution space, doesn't matter which one you use. Okay, it's a very, very trivial example, but that is sort of the sense of it. Like sometimes you would see very, very abstract things that a priori you have no idea how to handle them, but you can show that they're isomorphic to something that's very straightforward, and then you can use your results and techniques in that space. Okay, it's kind of like changing your coordinate system, right, in physics that we've often done. All right. So that sort of concludes the stuff I had written on this slide. So let's move on to, oh no, I didn't copy this. Okay, guys, give me like just a minute. I will need to paste something. So I basically wrote the notes, but I did not move it into the, because I keep a copy so that, when I overwrite, it doesn't destroy the notes for the next time. So I'm just doing that. Okay, so we have it here. What example were we looking at? Do you remember? Oh, we just started the next section, right? We started section 3.3. Which section are we on? 3.3, right? Okay. Yeah, sorry. I think next time we should split them a little bit and put everything in one. Oh, this looks new. No, this is fine. Right. Yeah, so we just saw this. So theorem 10 is, so we saw theorem 10, right? You can't see it, sorry. Okay, you can see it now. Good. So theorem 10, right? This is what we just did. And we looked at the story for why the dimension preserving thing, right? We looked at this vector stuff, and these are the same, right? This is where we were, correct? Okay. All right. So now we'll start 3.4, which is representation of transformations by matrices. Okay. So let's start. So let V be okay. So that's the story part. Okay. So in this section, I think I have a feeling there are two authors in the textbook, right? There are two authors in the textbook, and I think different people have written different sections. So they have different styles. So normally it gives you the theorem statement and then it gives you a proof. In this section, it just talks and it's like, oh, by the way, we proved this theorem. Okay, so the structure is a little bit different. So I'm just giving you a heads up. All right. So okay, so let V be an n-dimensional vector space over the field F, and let W be an m-dimensional vector space over the field F. Okay, so V and W are vector spaces as usual, and B is the basis for V. Okay, and B prime is the basis for W. Right? So far we've just defined the V species, and it says that if T is any linear transformation from V to W, then T is determined by its action on the vectors alpha J. So this we already saw. It's just sort of reviewing what we've already seen. So for each of the n vectors, T alpha J is uniquely expressible as a linear combination that we write here. So T alpha J is sum over I from 1 to m Aij beta j. Okay, so for each j, you can express in the new space. Oh shoot, I messed up this. This is I. Sorry, it's just that normally the indices in matrices, right? It's ij and then there's xj. So these indices match, but when they write it in for more abstractly, they tend to write the indices like this. So it's not the closest ones. But right, so what they're saying is that every alpha j one can write as a linear combination of the bases. So there's nothing complicated there, and you have this index j, right? Because for each j there could be potentially a different linear combination. Okay, and these alpha 1 to alpha mj are the coordinates. The coordinates of T alpha j in this basis beta prime. So this is fine, and accordingly the transformation T is determined by the mn scalars using this equation. Okay, so this is stuff that we've already discussed, because otherwise you break linear independence. We saw this, right? Okay, all right. So now let's look at some notation. So an M cross N matrix defined by this is called the matrix of T relative to the pair of ordered bases B and B prime. Okay, so this stuff is basically saying that if I can write any linear operator in this form, so I have some basis in the initial space, some basis in the final space, okay, and I write down the action of T on the basis elements, then these coefficients I'm going to call the matrix of T relative to the basis BB prime. Okay, this is just a notation. Is the notation okay? So abstractly, what I'm doing is I'm taking there is some linear operator T. Okay, it's an abstract object. I'm going to pick a basis in the initial space and the final space. Okay. I'm going to apply this linear transformation on every element of the basis in the initial space. Okay, and I will get some linear combination in the final space. And those coefficients are going to form the. Is that okay? There's nothing very deep. It's just to build some intuition. Okay. All right. So now our immediate next task, immediate task is to understand explicitly how the matrix A determines the linear transformation T. Yeah, I think we're sort of discussing this. Okay. So right. So suppose that alpha is some vector, okay, in V. So we can write it as a linear combination of the basis vectors. Then T alpha, one can write as follows. Then so this is just the definition. This is linearity, right? And now T alpha J, this is by definition. This is what we get in the end, right? That if you have a vector, the coordinates of this vector in the new basis would just be the initial coordinates multiplied by the matrix. Okay, and so you see now the matrix multiplication is in the regular form. So it's Aij xj, sum over J. Okay, and when we had written this down, you see here it's Aij beta I. You see, so here's the first index with the first index, here's the second index with the second index. Okay, so when you're doing everything with the coordinates, things are going to be like matrix multiplication. When you have coefficients and an abstract vector, then the summation is slightly different. Okay, there's something to watch out. This was T of alpha, right? Just something to be mindful of. You could also do it the other way, it doesn't matter. But then your matrix multiplications would become a little bit weird. So we want the matrix multiplications to be consistent. That is why we are defining the coefficients in this specific. Okay. Well, now if A is any M cross N matrix over the field F, then the transformation would basically be given by this. Then one can define a transformation as such. So you take any matrix A. Okay, what did we do? We said for every T, one can associate an A, right? Now it's doing it the other way. For every Aij, right, some matrix. Now it's going to associate a transformation, and it's doing it in the most trivial way. So it's saying that if you have any vector, then the way it acts on this vector is as follows. Okay, that's it. Any questions about this part? It's very straightforward. There's nothing all that interesting. Okay, so now let's look at theorem 11. So theorem 11 is basically just summarizing what we said so far. So V, W, B, B prime are exactly the way we define them. And it's saying for each linear transformation T from V to W, there is this M cross N matrix with entries in F such that T alpha. Okay, so now it's using this nice notation, right? So remember this notation for a vector alpha. So what was this notation? Exactly. So this was, say for example, we can write xi beta I. Right? So B prime is say beta i's. Right, so one can write this. No, actually, it's just let me write it better. So it's x1 to however many basis elements there are, right? Where alpha is a sum of, well, let's just say beta because we are writing the second one. Where beta is a sum of xi beta I. Right, so that was the definition. Is that okay? Okay. So now it is saying that we can basically all the discussion we had above, we can write it as follows. So T alpha, you write so you get a basis, or sorry, you get a vector in the space. In which space do you get this vector? T alpha is in which space? W, right? So in the space W, what is the basis? B prime. right? B prime is the basis. So for the basis B prime, T alpha is, so you get the coordinates in the B prime basis, and this would be the same as taking the matrix A, right, which is an M cross N matrix. So M is the dimension of W, N is the dimension of V, and then you take a vector alpha in B. Okay, so alpha is in what? In V, right? And V was of dimension N. So you take an n-dimensional vector in B prime, you multiply it with an M cross N matrix, you will get an m-dimensional vector. So everything checks out. Is that okay? All right. So there's like a very compact way of writing what we wanted to say. And furthermore, okay, so saying for every linear transformation T, one can associate this to this matrix A. And then actually it goes on further. It says that this correspondence from T to A is a 1-1 correspondence between the set of all linear transformations V to W and the set of all M cross N matrices over the field F. Okay, so both ways. All right. Okay, so now we continue then. So we have the matrix A is associated with capital T in theorem 11. Sorry, the matrix A that is associated with T in theorem 11 is called the matrix of T relative to the ordered basis BB prime. Okay, and what is very funny is that we just said this a few seconds ago. It's exactly the same as this. I don't know why the text repeats it. I don't know if I'm missing anything, but it's said twice. But okay. Well, so now the note is that equation 3.3 says that equation 3.3 is which one? Did I not write it? Oh. Okay, I think we would have to guess. I forgot. I don't think I wrote equation 3.3. Probably this one. Maybe. Okay, so equation 3.3 says that A is the matrix whose columns A1 to AN are given by AJ, where AJ is this object. I guess 3.3 is probably this one. I think it's probably this one, 3.3. Let's see. Oh no, it's here. That's the one. Okay, so 3.3 is basically this thing. Alpha J is sum over Aij beta. So what is this? Right here. Okay, so this is equation 3.3, and equation 3.3 is saying that. Sorry about the jumping around. So this is equation 3.3, right? So 3.3 is this, and it is saying that. So it says that the matrix A is basically a matrix whose columns are A1 to AN, which are given by this object, which is exactly this. Is that correct? Alrighty. Okay. So now if U is another linear transformation from V to W, and B is B1 to Bn is the matrix of U relative to the ordered basis BB prime, then CA plus B is the matrix of the form CT plus U relative to BB prime. Okay, so all this is saying is that, so if you had a transformation T, the corresponding matrix was A, right? So we fix BB prime, right? These are the bases. So T and U are both going from V to W, right? So if you have T and this is the association for T, and then you have U and this is the association for U. So then the linear combination, right? We already defined for linear operators, you can define a linear combination, right? So then the corresponding matrix would be, as one would expect, CA plus. Okay, this just follows from linearity. It's nothing very complicated. Okay, so to see this, what they've done is they've actually written it out more explicitly. So AJ, BJ, one can write as follows, and then AJ, one can write as C acting on T alpha J, and U alpha J, right? Just from this association we had above. Correct. And then that allows you to, because it's linear, you can take it inside, and then you basically get that it's CT plus U acting on alpha J. Right? And then you can use the definition. It's a very standard thing. Okay, so now let's take this formally. So the statement is that if V is an n-dimensional space and W is an m-dimensional space, for each pair of bases BB prime, for V and W respectively, consider the function that assigns to a linear transformation T the matrix relative to BB prime. Okay. Now this function is an isomorphism between the spaces between linear operators from V to W and the space of all M cross N matrices of equivalent. So it's sort of restating, in a certain sense, what we argued. Yeah. So we observed that the function in question is linear, and as stated in the theorem, it's 1, and it maps these onto the set of the thing, and so therefore it satisfies the requirement to be simple. Yeah. Any questions? Is it okay? Or a set of linear operators from V to W. So it's just saying that there is a very strong association, right, between linear operators from V to W and the matrices, these M cross N matrices. Right. So earlier we said that there is like this nice mapping and so on, and now we are saying that the mapping actually satisfies all the properties to assert that there's. Right. Okay. So let's see. Theorem 11 is fine. Okay. So far so good. It makes sense. Let's. Okay, we have about 5 minutes. So let's see how far we can make it. Okay, so now we focus on the representation by matrices of linear transformations of a space to itself. Okay? So we've been looking at LV comma W. Now we're going to look at LV comma V. We're going to focus on this part because it tends to be quite useful. And in this case, it is convenient to use the same ordered basis. Right? So we want to take B to be the same as B prime. So not only are we taking the same space, we're also taking the basis to be the same. So here's some notation. So given linear transformations and the basis as above, the representing matrix, we simply call them matrix of T relative to the ordered basis B. Just and since this concept will be important to us, we review the definition. So the definition would now, so we basically, instead of betas here, right, we are going to have alphas again. That's the, so it's exactly the same definition. And J goes from 1 to N instead of N, right, because the numbers are the same. Okay. So for every T, there would be an N cross N matrix. Okay. And note that this matrix depends on the ordered basis B. Okay, so it's not independent of the basis B, and then it's representing a matrix for T in each ordered basis for V. Sorry, and that there is, so for every B you can find a representation matrix. That's kind of obvious. And for transformations of one space into another, the matrix depends upon the two ordered bases, one for V, one for W. So it's just trying to draw a contrast compared to the previous case, because there you had choice of basis for V and W. Here, since we fixed B to be the same, we can just change one thing. Okay. Okay. So now they're going to use the following notation. So let T be above, and they're going to use this notation T sub B to denote the matrix of linear operator B in the order, linear operator T in the order basis B. Okay. This part is a little bit boring. It's just like repeating the same thing in many different ways. The important thing is that just as we have alpha for some basis B, now if we have T, which goes from, which is a linear operator from V to V, then we can talk about the representation of T relative to B. That's all it is. Okay, so then it says let T be as above. It holds that T of alpha in the basis is the same as TB and alpha. So I'll leave this as a homework exercise. Okay, it's just basically just apply the definitions you got. Okay, so example 13, and maybe we can stop with this example. I think that's a good place to stop. Okay, so let V be the space of n cross 1 column matrices over the field, and W be the space of m cross 1 matrices. Okay. Now fix any m cross n matrix over F. So V, W, these are columns, and A is some fixed matrix, m cross n matrix. Okay. And okay, so now let T be the linear transformation from V to W. So T of X is defined as AX. Okay. And let B be the ordered basis for B, analogous to the standard basis. So we're just saying that it's the, alpha I is just going to be zeros and one at some location, right? At the ith location, it is one, otherwise it is zero, right? Okay, and then similarly, B prime is the basis where you have Yj. So so this they're calling Xi, and this they're calling Yj. Okay, it's just the standard basis. There's nothing complicated. Okay, that's all they're saying. Okay, and then it says the matrix T relative to the pair BB prime is the matrix A itself. Okay, so we define T to be this object, right? That it is going to take a vector X, V, and send it to W by application of this matrix. Okay? Now the claim is that if you just apply the definition, then the representation of T in the basis B is going to be, I think, BB prime. Yeah, so this is going to be the same as the matrix A itself. So that is the claim. How do you see this? So we know that T acting on Xi is going to be just this object. Right? So remember we had T alpha J. This is how we had written it earlier. It was A Ij beta X. Right? This is how we had written it. So now instead of alpha, we are writing X. Instead of beta, we're writing Y. Right? We have not changed anything. So this is just from the definition of what it means. Sorry, what it means to have the representation. So I put a prime here. Okay, so we don't know what A prime is. We want to find what A prime is. Okay? So now what we're going to do is we know the action of this object, Txi. This was given to us, right? We were given a matrix A, and we said that Xi is basically just the standard basis, right? So when you multiply this, what you get is you get the ith column. So you get A sub I, the column. Yeah. Okay. And this one can actually write as a combination of A1, Y1, right, plus A2, Y2. Right? So if Y1 is just 1, 0, in this example, 0, right? So it is just essentially multiplying the columns, and that allows you to get the final result. So I'll let you check it at home. It's just a quick. Okay.